Chip, over to you. We have 30 minutes.
Thanks, Jim. He said that there's no other panel who'd rather be on, but I'm pretty sure he said about every panel. So, but I'm very excited to be on this panel because there are a lot of names that I recognize and haven't chatted with in a while, and I'm excited to hear. So, thank you, Jim, for the introduction. So, I'm teaching machining system design at Stanford, but I don't think there's a group on machining system design at Stanford, but maybe some of you here will join Stanford and start that group. Okay, so I think the panel is about the future of feature stores, and we have on the panelists here have been working a lot on feature store and also like related products. So I think what I'm going to start by, maybe do you guys want to start by introducing I know that some of you have been at the event, but I think I just gonna start.
Yeah, I mean, we can go around. So I'm just hosting it, Jim, and
yeah.
but we've been talking a lot about the whole end-to-end, you know, from evaluation stores to notebooks in production as well. So, you know, I think that the topic of conversation in this session has kind of spread beyond just feature stores, and that's fine. So that's
okay. So is there anybody here who hasn't given talk at the event?
No, everyone gave everyone's given a talk. So
okay,
so intros are done, I think. I
see. Okay, so that's great. So we can just jump right into default questions. So I'm not trying to get all the like business secrets out of you guys. So I think I'm gonna start with maybe like questions that may seem basic for a lot of you here. So I know that feature store is to help companies manage their features, especially to ensure consistency of features during training and inference. And I'm curious about like how do you ensure the consistencies? And because I know that a lot of companies, there is a different pipeline. For example, you might use Python during training and Java during inference. And then how do you ensure that the features are stay the same during both training and inference?
I can take it, or Attendu, you can take it. It's I can take it to begin with. I mean, well, I think one of the things that people say about, you know, ensuring consistency between training and serving is, firstly, in serving, you'll have the latest values of features typically. So serving clients will say, okay, I'd like the latest value. And sometimes there are edge cases where you don't just want the latest value, maybe you want yesterday's and the day before, but then you don't need to store all of the values, you just make that a new feature. So often what you'll have is, if I take it from a distributed systems perspective, we have eventually consistent guarantees on the consistency between serving and training. And typically, I think most systems will write to the serving layer first, and then have eventually consistent replicate to the offline store. And in our case, we're using Hoodie as an offline store by default, which gives you nice ACID properties for writes. So that ensures that if you retry, you're not going to have garbage data there. That's kind of a technical answer. Sorry. I don't know, Atendrea, not everyone is working on this, so I guess.
Is that a question for me? Sorry, I missed that. No, I think you kind of covered what you said was fairly on the spot, except I have seen many cases where, particularly for batch features, which are historical aggregates over sometimes many months of data, and typically you would have risk and fraud models where features and labels are pretty sparse. So you would typically go back many, many years to get enough data to train a model. In those cases, typically ML practitioners would first aggregate and materialize features offline and train their model, and later have those features available for online serving. The story is reversed though for near real-time features, where you make them available for serving first and later you backfill it for training. But you covered a good important point about storing aggregates so that you don't have to do computations like, you know, going back one day versus 1 week. So those kind of aggregations do help, and feature stores typically at the API layer, they would provide these kind of aggregations out of the box. And at least at Palette, at Michelangelo, we used to sort of log the data at the lowest granularity level, and we would provide the flexibility at the API layer to be able to do custom aggregates. So for the same feature, for example, number of rides taken, you could essentially, at the query layer, you could specify 1 day, 1 week, 1 month, or 1 year. And behind the scenes, we would just do the computations of course, that leads to other sort of scale challenges. And to sort of solve the online-offline parity problem, it's an interesting point about Python versus Java, because that's the reality of most ML systems, where training typically happens on Python. But at least in Michelangelo, like the core engine was Scala, because it was primarily Spark-based. And that kind of gave us the flexibility to sort of share common modules between the training and the serving ecosystem, because serving is completely Java. But because they're both JVM-based languages, we are able to sort of share modules between the online and offline. And that kind of solved part of the parity problem, where in-memory transformations on features, we could practically use the same function that's just written once, and we could use them in both training and serving.
That's a very interesting point. So you're saying like you have a common module like in neither languages. So like instead of choosing Python and Java, just go like Scalar. So like good compromise that neither side is happy, but it works for use cases. So I saw that David raised his hand. David, want to jump in?
Yeah, I didn't want to interrupt. I think the funny part here is that, everything old is new again, right? I'm very old, and I remember that, when we had these things called OLTP, and it basically, many of the same things that you saw there were here, right? You're providing clean layers of abstraction for the different roles in your organization. You're providing common locations, clean APIs, and all those kind of things. And more than anything, decoupling, right? Because the worst thing in the world is that you have a feature store, or you have a feature that you need, and in code you optimize that feature and it works. Yet when it comes to inference, or it comes to future deployments and things like that, it was optimized in a different way. I mean, the classic example I always toss around is, how you have a blank in your feature. What do you do with it? Is it null? Is it zero? Is it empty string that gets swapped out later? The number of times that I've seen that be mistakenly done is very large, and that's I just think that feature stores feel like a very advanced thing for a lot of data science and ML, and not just sophisticated ML, just generic data processing. But they are absolutely critical to any organization where all the stuff isn't happening in a single person's head.
I see. So it's saying that like it's important to like make sure that the feature extracted during inference are similar in terms of like maybe based on statistic extracted during training, like number of non-zeros, min, max.
I mean everything, right? Not just at inference. It's also the next person who comes along to implement it. If you're comparing models over time, if you're all those kind of things, all of those elements are part of your model pipeline, and that's why it's so critical to use something that gives you a clean interface, speeds your developers, but also provides normalization.
Yeah, so I think like based off the point that David has said, I think I'm just want to bring up a question that might be relevant to like all the monitoring services, and I think I'm looking at you, Josh. So I think like so you mentioned that data validation to ensure that data is expected, but I think like on the statistic and the data change over time. For example, is an average, a mean, variant change over time. Then how do you ensure that data is consistent to certain statistic when that statistic is changing? Josh, do you wanna? I'm not sure you have some thoughts about it.
I'm not totally sure I understood the question. So like, where are you trying to ensure consistency there?
So I see that like when I see it tools like Great Expectations to help you ensure that like the validation of the data, you do it by specifying statistic of the data, and if the data the incoming is deviate from the statistic, then you like there is something not right. So but the question here is just like, how do you specify those statistics, and what happened when the statistics are changing? Because when you define those statistics, you assume that they stay consistent.
Yeah, this is a really good question. I think like my view is that we don't really have the right framing of this problem yet as an industry. I think the challenge is like you can. So let's say that your goal is, look, I have a machine learning system, it's running in production. I can't get labels, or my labels are delayed or expensive. I want to be able to tell if my model still seems to be performing well. And so Chip, what you're pointing out is like, typically the way that people will tell you to do this is to look at the distribution of input features to the model, or maybe the distribution of predictions that the model is producing. And so the question is like, how do you know if those distributions are like within some normal range? And there's a few different approaches that people typically tell you to do. So one thing is you can just slap ranges on them. So you can say like, look, if the mean of this particular feature is, greater than some certain amount, or if like the feature all of a sudden has values that are outside of the range that it saw during training, then that's probably something I should be alerted about. And that approach is like, tends to be what works pretty well in practice. Like you just put pretty loose ranges around like, look, I know if, the range of this feature is like, in training was 0 to 10. And so if all of a sudden I see 100, then like that's really bad and we should get an alert about that. But what's tricky is how to make those ranges tighter. And one of the reasons it's tricky is that like, distribution distance and other metrics that you might want to slap on a particular feature aren't actually really what you want to measure when you're trying to monitor a model. Because if like the distribution, so like the high horse I'll get on is like people tell you to measure like the KL distribution between the training feature distribution and the production feature distribution, which is just like the wrong thing to do. Or sometimes they'll tell you to run a KS test. The problem with these things is like, if you run a KS test, and you have a lot of data and the data has shifted even a tiny amount, the KS test will very confidently tell you that the distributions are different, even if they're only shifted a tiny amount, right? Our machine learning systems are meant to be robust to tiny distribution shifts. If they can't do that, then we shouldn't be putting them into production to begin with. So like your KS test saying that, P equals 0.001, that this distribution is shifted is totally useless piece of information for me as a model developer. I think what we need to move toward as a field, and this is kind of where I think like theory needs to catch up with practice a little bit, is I think the right way of framing this problem is in terms of like approximate model performance. So I think like what I as a model developer, like model operator want is, I want to know like, okay, given all the information I have available to me about what is happening with this model in production, the distribution of the inputs, the distribution of the predictions, any labels I do have, any other context, maybe even from our users or our model operators, what is my best guess as to like the range of performance that this model might be hitting? I think if we can build a conceptual framework around that, these types of statistics will be a lot more actionable to us in building machine learning systems.
I see. So what I'm that is very thanks for like a really great explanations. I feel like it's starting to get so many terms I need to note down so I can look it up later. So anybody want to add to Josh before we move to the next question?
I'm just going to ask Josh, I mean, because, if you're not going to rely on the automated approaches, we have a lot of ML ops people in here, and they think they can automate the whole thing. But what you're kind of arguing is that, well, you need higher level knowledge about the performance of model, the KPI that might relate to something outside of the system, but we need to pull it in. Can this be resolved with the ML ops vision of automating everything and software engineers doing everything?
Well, I mean, it depends what you mean by automating everything, right? Like I think we're a long way off from like machine learning systems that you can just like toss into prod and have them work for forever. I think that's a bit of a stretch from where the technology.
Yeah, automated monitoring is really what I'm talking about.
I think the role that humans are going to play in this process hopefully becomes a lot more constrained and a lot more well-defined than it is today. And I think a lot of what people will need to spend their time doing is kind of exactly this question, right? Is like, look, we have a bunch of information that gives us context on how this broader system is performing. There's some automations that we can build on that, right? Like, I know if all of a sudden one of my features completely nulls out, that's probably an issue that we can fix, and we might even be able to fix in an automated way. But the subtler cases are like the things that you can't really anticipate, or the harder to detect shifts that really impact model performance, but not in a way that you can catch with an easy to write automated test. And that's, I think, like one of the main roles that people are going to play in these systems for at least the foreseeable future.
So I have a couple of questions related to this, but I saw that David also have some thoughts on it. So I want to make sure that, yeah, go ahead.
Sorry. Yeah, I mean, I think Josh is exactly right. I think that there are two, once you get your feature store, I think there are two hidden potholes coming soon for machine learning and data science. And those are statistics against your data, and not statistics on, just averages. It's got to be everything, right? Outliers, min maxes, mean mode, everything like that you trained on. So you say this model was trained on features that had these statistics. And if your inbound data changes substantially from the statistics, you need to call a halt. It doesn't need to be sophisticated. Just say like, whoa, something changed here. Exactly like Josh just said, this nulled out, or this, is showing, 20% more outliers or something like that. So I think folks really need to look at that. There's a lot of work from TFX that did this and so on. There are a lot of great tools out there. I'm a big fan of Great Expectations. I don't know if we're allowed to pimp stuff that I am not involved with, but like I just love what they do. And then the other one is schema. Hard identification of schema of your inbound data as well. So say this is a int, this is a string, this is a whatever. Again, it doesn't have to be a lot, but like the extent to which you can build that in before you do your processing, it will save you countless hours of debugging and testing and things like that. And it's not hard. There are lots of frameworks out there, and it doesn't require a lot, right? It could just be like, hey, I loaded this data frame. Here's what I expected this data frame to look like. Fail, throw an error and say like, this scheme is off.
David, what about roles that Patrick talked about? Like schema is not enough. You have a role. This is a categorical variable, a numerical variable, an embedding that Laurel had. Do we need that as well?
That you're starting to get into advanced stuff, and I'm not saying no, right? It will absolutely. The more that you can build sophistication in here, the more it will make your pipelines reliable and speed your developer time and minimize, improve the ability to do automation and trust and things like that. So absolutely, I think those are all good. The problem is, again, I don't want to badmouth anyone, but the vast majority of stuff today is happening with nothing. No schemas, no error checking, no anything. And then all of a sudden the model went sideways and you spend 2 days realizing that, we now, do zip +4. And so it's no longer just a digit. It's a digit with a plus sign in the middle. I mean, like that kind of stuff. So it's just something to be aware of.
Yeah, so I think like jumping just off, right? You guys talking about like how so I think like the thing about retraining the model is that you want to like adapt the model to certain failure modes. And so I was actually a marketing company told me that the majority of the performance changes they see actually don't require retraining because they happen because of some human errors, because some bugs in the pipeline. And so like in the work, have you tried to like categorize different failure modes and like based on maybe the causes or like what is needed to be done to fix the failure modes of the ML system in production?
Yeah, I mean, human error is definitely the most common one. But data distributions are not static. And so I think like we should, like as an industry, we should figure out how to catch human errors, which are easier to detect and hopefully easier to fix really robustly. But I don't think that that's going to be enough.
Have you noticed similar things with systems? Like, do you see that human errors are like going up or down over time?
One thing I've noticed is there's just a lot more machine learning in production now than there was a few years ago. Like when we started teaching the full stack deep learning class in 2018, pretty much all of the people that attended were like production, like wanted to put ML in production, but hadn't actually done it yet. And then the last time we taught the class, the majority of the class were like folks that were doing ML in production and we're trying to figure out how to do it better. And so like my perception is that, where we were at as a field in 2017, 2018 was there's a lot of talk of like, oh, ML is not living up to the hype. Like there's this really cool technology, everyone's hyping it up, but no one's actually doing anything useful with it. Now I think the pendulum has swung back the other way, and we've corrected for that by like just YOLOing tons of models into prod without really a whole lot of like engineering discipline about how we do that. And so, yeah, I think the amount of like human error has gone way up because like, for for kind of understandable reasons, like we're being less careful in a lot of cases about how we get things into production, which, there's some good aspects to, which is that like machine learning is actually doing a lot of useful stuff now, a lot more than it was a few years ago. But I think, we need to swing back the other way a little bit and add back a little bit of operational rigor and control about and engineering discipline around how we do these things.
But there is one mechanism that Laurel talked about quite a lot, embeddings, and they're very forgiving to mistakes, right, Laurel? I mean, you can miss some values out of, they're kind of, if you're doing named entity recognition and there's some mistakes in the input vector, it's kind of forgiving. Is there an alternative story here?
I mean, like relating to a couple of things that folks have talked about. So my so the Overton system, which was at Apple, which was something that my boss worked on some, a couple errors that I think he noticed a lot in terms of getting those sort of embeddings deployed. Going back to schema, they enforce like very strict schemas as inputs to how to train these things, because I think they noticed just like kind of there were a lot of user errors in terms of even building and getting the training data ready for these embeddings themselves. I mean, now once you have an embedding, right, they can be more, you can also train them to be more or less robust to different kinds of noise. You can add noise and training to make sure that values go outside of a normal range, that things are okay. So in that sense, like one null is less problematic, but you get a lot more subtle errors that need humans in the loop to understand. Models pay attention to spurious features, correlations in data that as an engineer you could control for that, because you can say, hey, look, don't look at this feature, just use this one. But these models, it's much harder to detect these things. And so in that sense, like you need a much more rigorous testing at the end of it, right? These models are black boxes, and I don't know if we're ever going to be able to say, oh yeah, look, embedding value at position 6 and 7 is the cause of it. Like, I don't think we're going to get there, but I think we need to start treating these things a little bit like you do with a black box, testing your own code, right? I mean, that happens all the time. This is the same thing. You need to have rigorous testing on the inputs, making sure that there are, again, the right schema. I do think some of the distribution shift is pretty important here too. And then also really rigorous testing on the model outputs, right? I think there was a really interesting blog post that came out from, I think the folks at Tesla who were talking about how when they do models, they have this suite of tests, and any model who fails a test doesn't get deployed, right? And they make sure that performance is improving over time, and how it's this life cycle of how to do it. And so I think that's where I think you need that for feature stores, and I think you'll need that for embeddings as well.
Thank you, Laura. I think we have a very interesting questions from Ping. I'm sorry, I don't know the name Pengui. Please let me know if I said it wrong. So Pengui is asking, like, how far back do you usually need to go back to for the training pipeline? Like, so I guess they're talking about like what data. Yeah. So like, what data do you need when you retrain the model? Is this like a month, a day, or how far along? So I think I have a feeling this question is like open a can of worms. So I think we'd love to hear your thought on it.
Yeah, I can maybe just chime in. I think, yeah, just the short answer would be, I think it depends on the use case and also the type of the feature. Say, for example, then you want to compute the act of, the number of how you defined as fraud occurrences. And if you aggregate over a week, you would likely get a 0 value, even for a month. And even more rarer features are for sexual assault run at just are so rare, many years sometimes, to get enough of a signal in your feature set. Let me know if my connection is weak. Or if I'm breaking off, you can hear me.
Yeah, we lost you for like a couple of seconds. It's good now.
Oh, okay. Sorry, my internet is bad. But yeah, the short answer is it depends on the kind of feature. And yes, the solution is to do as much aggregations upfront, offline, so that it doesn't affect your real-time serving pipelines. But yeah, it depends on the use case and the kind of feature. And aggregations vary from like 1 second to 1 year is typically what I've seen.
Yeah, I want you piggybacking off this answer questions. It's something I'm curious about. So I saw some merging services who claims that they can tell you not only when to retrain, but what data to retrain on. So how legitimate is this claim? And how hard is that to do so?
When to retrain? I think, you know, there's kind of a vision out there somehow that you can monitor models in production. You can look for automated ways for, you know, finding drift in data or in concept drift. And then it sends an event back to a CI/CD pipeline, which will, you know, pull in the latest features that haven't been trained, the model hasn't been trained on. We train the new model and then we run the automated training pipeline, and no human touches this. And I think we kind of all agree that at this point, we're not quite there yet. I think just to touch on Pengu's point one little bit, one thing that's a little bit difficult when you're doing real-time feature engineering is if you have a streaming pipeline and you want to go back in time and your streaming pipeline is hooked up to Kafka or Kinesis to get the data, you know, you do have to think about that a little bit, decouple your connector to wherever you're getting the events from. So maybe you're going to have to go to a data warehouse or a data lake to go back in time to get the data, but you still would like to run the same logic again. So that's just something that the data engineers might want to think about when they're designing their systems.
So I just want to touch on a point that I think Josh mentioned earlier about that, like in the field, like research is still catching up with practice. And I want to hear, especially from Laurel, as in you're working a lot in research right now, like why is that like research seems to be like behind practice? Like, is that really hard to do research in this area?
That's a very interesting and I think more complex question. In terms of, I think some of it is both in terms of motivations, like especially for sort of you know, academics, what kind of things we're interested in. I think some of the issues, and I think you saw this a little bit with that diagram that I sort of had in my talk about, like the ML code being actually a very small portion of what actually is required to get a model deployed. And this is something that there's a term that's called modelitis that my lab likes to use, where I think engineers, like, it's really fun to play with model code. Like, it's just fun to, like, you know, use different architectures, use different inputs, like make this behemoth monster thing that like does really cool stuff. Like, I mean, that's what's fun. Like, I like to do it, students like to do it. And so there's something about, there's a gap between, hey, look, you have this thing, but like, that's not actually what it takes to get deployed. And I think sometimes people don't realize that. Sometimes it's hard. Like, it takes a lot of effort to understand what's actually needed. And so I think some of this is a disconnect between what sort of is immediately fun and useful versus what's like actually something that can actually, you know, be useful in production environments. And so that's why I love that diagram, because it's something here where another reason why some of these, I think, self-supervised pipelines are pretty interesting is that they actually do use fairly standard models, right? Like, and I know some systems, they don't let users to touch the model. They're literally like, you tell me the inputs, you tell me the training data, and I'm going to basically close off any of the fancy model connections. Like, you don't get to implement some crazy attention, blah, 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 that like is going to make it impossible to debug. I'm standardizing it because it works and we know it works. And there's something that's kind of interesting there, but I think that's a reason why it's a little tricky, is because, you know, students like to do the fun, exciting stuff sometimes, and there's a lot of work to getting it actually deployed. Yeah,
I totally agree with you. I think I got notified that we have 2 minutes left, and I think I would like to like end the questions that I actually been asking by companies a lot. So they were like, something like feature store and monitoring are so essential to their workflow that they are hesitant to like use a third-party service for it. So like, so if you guys probably seen it a lot in the work talking to customers, and what advice do you have for companies who are trying to decide between like whether build or buy for services like feature store and monitoring?
We have a panel coming up on that, so that's going to be another really interesting question. I think I'm biased, so I'll probably take out of this. I'll step out of this particular discussion.
Why are you biased?
We're a vendor, just in case you don't. We sell a feature store, so you know my answer is obviously going to be.
So everyone should buy it. Everyone should buy it. Yeah, sure.
No.
That's true. Maybe I can take a more purist sort of approach to this answer. At least from my experience with Michelangelo, I've sort of noticed the reason why people sort of adopted why people chose to onboard to a system like Michelangelo. And first thing was, of course, the scale at which the palette in particular is able to serve features. And over time, we were able to build a very, very low latency serving system. So I think that was one of the key reasons to hook data scientists onto a system like Palette, because they didn't want to solve the scale problem. And scale is like an art which is constantly evolving with the business. And like the rise of Uber Eats and during the pandemic was also a great example of how we had to scale Palette to double its capacity, like tens of millions of requests per second across thousands of models. So that's one piece which sort of is very attractive for data scientists, that they don't want to solve the scale problem. And the other is one reason to sort of, I guess, build versus buy could also be based on where in the life cycle you are of your machine learning. Typically, if you're brand new and you're starting your ML strategy, it's great to go for a feature store because it sort of organizes the way you manage your machine learning data. But the only oddity or the caveat there is, if you already have a way you do feature engineering, it's a little bit of the novelty of a feature store is a little bit of a mind shift on how you would use features for ML.
I see. But so like I think Michelangelo is so like a little bit of a different example here, because you guys don't sell it outside Uber. It's like on the customers, like internal customers. It's so actually we run out of time. So thank you so much for all the panelists for the participation. I think I actually learned a ton from this. And for people who want to hear more build and byte, please check out the upcoming panel with Jim.
Yeah, we also have a talk on Palette and Michelangelo in the next session, so you can find out the absolute latest, and we'll see what's happened, if it's fallen apart since you left that, or are they still surviving?
I think they're good.
I love your top, Patrick, as well.
Thank you.
Very good. Thanks, everyone.
Thanks.
We're gonna have a break.
Thanks, everyone.